Okay, today I'm going to be recording me working the example lens diagram problems. I haven't used Screencast in over a year, and I don't have my external headset with microphone with me, so I apologize if my audio quality is not the best. Let's go ahead and get started. So there are, I think, 6 that we're going to work together. I've already worked this one because this isn't an actual ray diagram problem. It's not having you find what the image of an object would look like. It's just showing you how a convex lens works. Remember that convex lenses are converging. They work similarly to concave mirrors. Alright, let's go ahead and get started on working this one down here. We have our object, which is way out past 2 times the virtual focal point. Lenses, again, have 2 virtual focal points. F prime is the virtual focal point, and regular F is the real focal point. Alright, so the first thing I want to do is label the 2 sides. For lenses, the left side of the lens is going to be virtual, and the right side is going to be real. This is because for a lens you expect the light to pass through, so light that has passed through is real, and light that ends up back on the original side is imaginary. It's our brains doing silly things, so that's virtual. The rules for drawing these are very similar to the rules for mirrors. You always start with a parallel line. This parallel line is going to get refracted through the real focal point. So there's our initial line, and then here is our refracted first line. The second line we're going to do goes through the virtual focal point, and it gets refracted parallel to the axis. These 2 rules should seem pretty familiar. The third rule is actually the easiest. You do a line that goes to the center, the optical center, which is O, and then that line just keeps traveling straight on through like this. We have a clear intersection, which is awesome. That means we know that's exactly where our image is going to form. So once we have our image, we're going to use the same 3 types of descriptors that we used for mirrors to define this image. Sorry about that. We're going to say that this image is real because it's on the real side of the lens. It's inverted because the image is upside down from the original object over here. And then it is smaller because it's not as tall as the original object. Okay, now these next 2 are going to be very similar to that one with just kind of one important difference. We're going to run through these pretty fast because they're exactly the same rules. First line is parallel to axis, then it's refracted through the focal point, then we're going to have a line that's through the virtual focal point, then parallel to the axis, lastly to the optical center, and straight on through. So again, we have a clearly defined image, goes right there. This image is still real, it's still inverted, but because we were on top of twice the virtual focal point, this is somewhat of a special case, and in this special case, it's actually exactly the same size as the original image. That's kind of hard to see, but it is true. Alright, so let's move on to looking at this one. Parallel to axis, through the through the real focal point, through the virtual focal point. Oh, this one is worth looking at for a second. You do draw until where the mirror would be, even though in our picture the mirror doesn't actually extend that far. So we go through the focal point to where the mirror would be. That's refracted parallel. I'm going to have to make my lines a little bit longer there. And then lastly, we go through the optical center and straight on through. Clear intersection. This time there's something pretty noticeable about our image. It is still real, still inverted, but it's now significantly larger. So there is actually a pattern there if you look. For this one, when we were way far away from the lens, it was smaller. When we were at exactly 2 times the virtual focal point, it was the same size. And then here, where we were between 2 times the virtual focal point and the virtual focal point, it was larger. That pattern will continue to some extent, in that where the object is located is going to change what the image looks like. Alright, well on this page things start to get kind of weird. Our pattern breaks down. Let's go ahead and start looking at that. So as always, we have our virtual and our real side, and we're going to follow the same rules. So we're going to start parallel to axis, go through the real focal point. Now here comes the tricky part. The second one is supposed to go through the virtual focal point, but the object is on top of the virtual focal point, so we can't draw that line. So we have to skip straight to line 3, which is through the optical center. So we go through the optical center, and then that line just keeps going straight, as always. Here there is a problem. These lines do not intersect ever, anywhere on the real or virtual side. That's because these are, in fact, parallel lines. Parallel lines will never intersect, which means that this is the special case where you have no image formed. When the object is directly on top of the virtual focal point, no image formed. Alright, well now we've moved from being on top of the virtual focal point to between the virtual focal point and the lens. So let's just start with our same rules. Virtual side, real side, parallel line, reflected through the real focal point. Then, this is the weird one. We're actually lining up with the virtual focal point, but instead of drawing down towards it, we draw up towards the lens. That gets reflected or refracted parallel. And then as always, we have the one that goes through the optical center and just keeps on trucking. Now, these do not intersect on the real side of the lens. However, they're not parallel. They do intersect somewhere. And our brains are really determined to figure out where that intersection is. So our brains just kind of start making things up. Our brains say, well, if those had traveled in straight lines, they would have come from back here behind the lens, like this, and there would be an intersection. Now, I clearly am not ending up with a distinct intersection, and I think the problem is with this line here. I don't think it's lined up well with the virtual focal point. So the beauty of doing it on a computer like this is I can just kind of do some finagling, try to get things lined up a little bit better, lining things up. And I'm still not able to get it perfect, but I can get it pretty close. So, we have a very different image this time. Let's talk about that image. It's virtual because it's occurring on the virtual side of the lens. Our brain had to make up these dotted lines to get this image. It's upright. because it's the same orientation as our original object, and it is clearly larger than the original object. This is the only time a convex lens will create a virtual image is when you are closer to the lens than the focal point. Alright, now we're on our very last lens. This is a concave lens, which means it's a diverging lens. It behaves like a convex mirror. Some things are still the same, the real side versus the virtual side, but which focal point we're worried about is now going to be switched, and I'll show you what I mean. So we always start with our line parallel to the axis. For the convex mirrors up there, we would next go down through the real focal point, but for this we're actually going to go through the virtual focal point. Now, we want to line up with the virtual focal point, but the only piece of the line we care about is that one. Then, we're going to go with our second line. We would normally go through the virtual focal point, but with a concave lens, we're going to go through the... Sorry guys. We're going to go through the real focal point. This actually extends all the way over to here, but we only care about the part that extends as far as the lens. That one is going to get refracted as usual, parallel to the axis. The third one, always the same. It's our best friend. To the center, to the optical center, straight on. Now, again, these do not intersect in real space, so our brain does more of its funny business. It says, okay, I think these intersected somewhere. I think they came from behind the lens in a straight line. So we're going to extend all of our refracted rays in a straight line. We do, in fact, have an intersection. And that's where our brain sees the image. This image has similar characteristics to the one we just did. It's virtual, it's upright, but it's now smaller. It's worth noting that while we did like all these different examples of the concave or the convex lens, the convex lens had like 6 different outcomes. The concave lens only has one outcome. This is the only possible answer you can get. Virtual, upright, smaller. Again, this is exactly the same as a convex mirror, where the only possible answer was virtual, upright, and smaller. This is why I said that if you understand mirrors, these lenses should not be very difficult. But if you're still struggling with mirrors, you need to go back and watch those videos instead of trying to struggle through this one.